have the pleasure of introducing our next speaker. So you know him by Jiba on Kaggle. He is, in my opinion, one of the OG Kaggle grandmasters, somebody I looked up to significantly as I was on Kaggle. Gilberto works as a senior data scientist at NVIDIA. Prior to NVIDIA, he worked at Airbnb and Petrobras, Brazil, as a data scientist. He's well known for his extensive track record in winning machine learning competitions and has held the #1 position at Kaggle for more than 2 years in a row, and holds a master's degree in electrical engineer from UTFPR in Brazil. So, Jiba, welcome to the stage.
Hey, hello everyone. Nice to be here again in another Kaggle Day. Is my third one. Every new Kaggle Day is very fun, very challenging. We can learn a lot, and I'm happy to be here again. Okay. Today, I'll talk about recommender system. But first of all, I would like to introduce myself. If you don't know me, my name is Gilberto Titerix. I'm from Brazil, and I've been doing Kaggle for more than 10 years. I got some golden medals in the competitions. I prefer to compete in this tire here. This is the competition one, but there are 4 tires in Kaggle, right? But I'm specialized in competitions. I won some of them. And that's why I'm here. I'm here to share my knowledge with you, especially if you're a novice. Doesn't matter if you're an expert, but I'm here to share, right? So today it's Recsys, right? Recsys is about recommender system, and every year there's this conference, Recsys from ACM, right? And that conference every year promotes a challenge, a competition, like Kaggle, right? Our team in NVIDIA won the last 2 years, and this year we got the 3rd place. So I'm very proud and happy about that. And I'm here to share our 3rd place solution from this year competition. So our team in NVIDIA is a merge of 2 internal teams, the Merlin team and the Kaggle Grandmasters of NVIDIA team. We have 4 Kaggle Grandmasters in the team and 4 NVIDIA Merlin members that they took part of that competition, right? So we shared knowledge internally, we compete together, and we got the 3rd place. Okay, recommender systems. Recommender system, I think it's the main topic of the event today and yesterday. It also was part of the challenge yesterday, right? And our Recsys is present of our lives, of daily life, every minute of the day, right? Everything is about recommendation nowadays. We can find recommendation in the movies we watch, in Netflix and Amazon. When you surf in the internet to buy something, probably you're going to see some recommendation based on some Recsys system that's running online. But everything's about recommender. The friends you made in the social networks, if you're going to purchase something, the advertisement you see is based on a Recsys running online, right? There are many different types of Recsys. I will be talking specifically in session-based recommendation tasks today. What is a session-based recommendation, right? It's basically when a user interacts with something, right, for a period of time, a predefined period of time, and have some interactions with it. But how to define exactly what a session is depends on the company, depends on who is defining what it wants, right? For here is just 2 simple examples from the same user. First example is looking for TV, the session one. So the user can surf, for example, in the web, search for 3 TVs, and then it stopped the interaction with this website, and we can define this as session, right? So the session will be defined by 3 items visualized. And then 5 days later, the users start to search for cell phones, look for 3 cell phones, and then stop interaction with the website, and this is defined another session, right? But a session can have multiple definitions. For example, we can define a session if users stop interacting with the website for 30 minutes, for 2 hours, or we can define a session, but all the interactions user had with the website during the entire day. So it depends on the business, right? It is a business defined definition. This is a session flow. This is a usual session flow. For example, the user are looking for that dresses. So it visualizes 3 items in a sequence. Then it visualizes again item 1, right? And in the end of this search, that session, the user purchased item 4. This is a very common to happen. Item 4 is not on the previous session data. It can be an item out of the session, or can be an item visualized in the session, so it doesn't matter. What defines the session is the user interaction during the period of time, and ended or not with a purchase, right? Now talking about the competition. The competition was hosted by Recsys, and they gave us 7 months of training data plus 1 month of the test data, 18 months the total, right? So they split 1 month out, the last month of the period for the test set, and then this test set was randomly split in 2 other test sets. The first one is the public one, and the other one is the final test set. The public test set is the one evaluated during the entire competition period, and the final test set is they make it available only in the end of the competition, right? To avoid overfitting. So basically, we have all the training set to work during the competition period that run for approximately 2 months. This is an important rule, not allowed to fit modules using the test data. What happens in the Recsys, usually we have the session items. They are presented in a sequence. Depending the module we train, you can train a module to predict the next item, for example, right? The next item going to be visualized or purchased, doesn't matter. If you use the test data to train a model, you are overfitting our models to the test set. But in real life, the test set is not available. It's future information. We don't have it in real life, right? That's why it's not allowed during this competition to use the test data to train the models, right? So this is very important, because if you use the test data, we got a boost, a huge boost in our scores. The boost occurs mostly because we are overfitting to the training. Training can change in 1 month, in 1 week, depending on the business. So it's not allowed. Okay, just to have an idea, a better idea of the data set, we have the 3 data sets: the training set, the 2 test set. Training set is around 1 million sessions, and the 2 test sets around 50,000 sessions each, right? So as I said before, the training set ranges from January 2020 to May 21. The both test sets is just June of 2021. Number of items or number of products available for this data set is around 28K if you take all the train and test set. But of course, we are talking about products that can be released every week. So for example, products that exist in the training set may not exist in the test set, because a test set period is after the training, and after the training, products could be released on that month, right? So we have that cold start problem as well, because there are items in the test set never seen in the train set. In average, the session length for the training set is 4.7 7574. It means, in average, each session in train set have 5 items, right? In the test set, it's a little bit lower. It's 4.5, and I will explain why test set distribution is different. But to explain that, I need to explain how they build the data set, because they clean the data set. This is a session, a raw session. They provide that example in the website. For example, we have items visualized, 5 items visualized, then an order, right? And then 2 more items visualized. Okay, when there is an order, they select just one item of the order to be the ground truth, to be the label. So they completely discard the other. In this example, they use item 4 to be the ground truth. So what they do here, the first time the item 4 happens in the visualization history, they cut the data set here. So we don't have item 4 in the history of the user. They remove the item 4 because this is the ground truth, right? They want to do that to avoid leakage, because different from the competition yesterday, that is a re-ranking task. This is not a re-ranking test. This is just a ranking test, right? Yesterday, all the labels are contained in the user history. This is not true here. They remove the labels from the user, so they just leave the search history previous the first time the user saw the item they purchased, right? And more than that, here, there's an additional rule they made only on the test set. So this is how the train set clean data was available for us to compete, right? We have a lot of items removed, and this clean data was sent to us to train our models. Yeah, this is just to have an idea of the distribution of the length of the session and how the data is presented to us. This is just a single session, session 18. We have, user have visualized 3 items in that specific timestamps, and then user ended purchasing that item there. The item purchase is not present on the user history, right? Very important, the session length distribution with sharp edges is very interesting, because I said the train set have 1 million sessions, but 300,000 sessions have only 1 item in the session history. So it's a very challenge to predict what user is going to purchase with only 1 visualization of 1 product previously, right? If you sum the distribution of session length 1 and 2, we got almost half of the train set with session length 1 or 2 only. So it's very small history to predict the purchase, right? So the host is focusing in exactly small session lengths. Okay, that's what I said about the test set. Additionally, what I said before, in test set, they cut extra 50% of the items in the history. So they randomly cut 50% of the items in the test set to make it even harder, even more difficult to predict the item purchase in the test set. This information is very important when we are modeling for this competition. Okay, this is another information they provide us in an extra data set, item description. So basically, we have the item history of visualization, but for each item, we have some description also. For example, color, size, any kind of description that we can imagine they provided, but anonymized, right? They don't tell us if the numbers they give us this kind of item description. They don't tell us what each number represents, what each category represents. Here, for example, item ID 2 have a category 56, what is 56? Can be anything. Can be color, can be size. And adding to that, there's a feature value also, right? So it's a completely anonymized representation of the item. Why they did it? Maybe they are looking for a very general solution for this kind of problem, right? Something that can be used to anything. They don't want us to overfit, for example, to build some feature engineer that takes color into account or the size or something like that. They want something very generic that works good in every situation. The metric they asked to optimize is the mean reciprocal rank. It's very similar to the metric given yesterday in the competition, the map. The difference here is the mean reciprocal rank takes into account only one ground truth, one label. It just takes the rank of your predicted item, and it takes the inverse, the reciprocal, and then take the average for all the sessions. It's pretty straightforward. Basically, if you have a mean reciprocal rank of 0.1, it means that in average, our solution predicts the right item in the top 10 of our prediction list, right? 0.1 is top 10. If your reciprocal rank is 0.2, our prediction is very good. The item is present in the top 5 every time in average. Okay, so given the test set, they cut an extra 50% of the items visualized. It's very important to have augmentation for any model trained in this data set. So the first thing we talk is augmentations, right? How we can augment the data. We need to build a very customized augmentation set here to make it work. And we think about that 8 types of augmentation. We tried that 8 types of augmentation. It worked with this specific data set. It's very customized. But for example, taking account they remove 50% extra of the items in the test set. We try to reproduce something similar here, but also some that try to remove some of the randomness also on this data set. Because adding to that, they pick only one item to be the ground truth, right? Even if the user purchases multiple items, they pick only one for the ground truth. There's a lot of randomness in this data set. Running augmentation with all the algorithms is very important here. For example, we have the original sample here in the items visualized 1, 2, 3, 4, and ended purchasing item 5, right? For example, the augmentation B, swap the last viewed item with the target. We make the last viewed item becomes the target, and we give that data to the model during the training time, right? This is one type of augmentation. But there are other types, always trying to randomize the item order or swapping with the target, something like that, right? Or just shuffling the items order. All these augmentations help it boost model performance in this task. Very important, validation scheme, validation strategy. This is a time series, of course. It's based on fashion e-commerce data set. So trends matter, time matters here. And the test set is on June 2021. We think a lot of strategies, but we ended using this specific strategy here because of seasonality, trending, and the time dependence on the data, right? So we split a validation set close to the test set period to be more similar items. So during the validation and test period, right? So we pick one entire month for the validation set. We are not doing a 5-fold cross-validation here. Even if you split by time, it's not going to work because we are looking to build a model that predicts more similar to the test set. So that's why we pick the last month on the train set for validation, right? And adding to that, we have two validation sets. One is the original data, and the second validation set, we run the same strategy they made on the test set of removing a random 50% of the items from the user visualized items, right? So we have two validation sets, one trimmed and the other one original. And we calculate the metric for the two when tuning hyperparameters, tuning the models, doing feature selection, and selecting the best models, right? Then for submission, once you have good models trained, tuned, and everything else, all the best models selected, we retrain everything on the full training set before generating the inference in the test set, right? The validation is just to tuning, to validate it locally, to find a good and robust strategy to calculate local validation. This is our solution. It's not simple, but it's very fun if you like stacking. It's a three-stage stacking solution. We built dozens of level 1 models, but we ended selecting 17 single models on the stage 1 here. The 17 models have basically 6 different types of models. We have statistical models, nearest neighbor models, gradient boosting, RNNs, MLP, and transformers, right? What's the idea here? We built that level 1, stage 1 models here. We validate on the validation set. So we generate the predictions for the validation set, right? We have all the predictions, our guesses for the validation set. Then we pick the guesses, the model predictions, and we feed the stage 2 models, right? Just with the predictions. And then in stage 2, we train 3 more models on the predictions. That stage 2 output more candidates, probabilities for feed a stage 3 model that do a ranked average, a weighted average of stage 2 predictions. This is a classical stacking approach, but with 3 levels. Usually stacking can be infinite levels. Usually it's 2 levels, but here we found better to use 3 levels because with 3 levels, we get the most of the metric. I will talk better about each one of the stages and models in the next slides. Okay, the first model we built, as I said yesterday, is very important to build a baseline. The first model is a baseline. It's a very simple model that we need to have a baseline to improve based on that, right? So what I did here is we calculate the probability of occurrence, for example, probability of purchase of one item given one item visualized, right? It's basically probability. But then we weighted it by time. Items viewed last have more weight than we view items viewed first, right? So probability weighted by a time decay, right? Giving more weight to more recent items visualized. This is a very simple, there's no tricky building that, and the results is just sorted by the probability of each item to be purchased. This generates a very good baseline. I will show later the scores of all the models. Also, we have a session-based neural network. There's some recent papers showing that approach sometimes can beat even deep learning models. It's not the case here. The case here, it produced good results, better than the statistical model, but not better than deep learning gradient boosting model. So it basically finds similar sessions based on item ID and the time difference between visualization of items, right? It just run a nearest neighbor on that and retrieve a list of similar sessions with similar items purchased. Pick the similar items purchased and generate the results here. The difference is it can be run. We run for the last 120 days, then last 90 days, 60 days, and 30 days. We ran 4 different models for that, and we averaged the 4 results to generate that specific model, right? We ran for different periods of time in the train set. We didn't use all the raw training set, we just used that 4 different ranges of time. We observed for this specific model, training on the last 30 days performed better than the model trained on the last 120 days, right? Specifically because this data set have a very high time dependence and seasonality patterns, right? So fitting that data more close to the test set usually is better. Okay, we have also a gradient boosting decision tree. We trained 2 models, an XGBoost and a light GBM, but for gradient boosting, it's a very specific case here. It's different than deep learning because here we need to transform the data set to a binary classification data set, similar what we most of the things did yesterday, competition, right? So basically for each session, we convert each item ID to a row in a data set, in the training set. But here there's an issue. Yesterday, the label is present on the item history. Here, we don't have the label present in the item visualization history. So what we need to do here, we need to add negative samples to each session. So we have the items visualized by the user, but we need to add some negative samples in order that the label is contained on the negative samples, right? Samples that are retrieved by another model, okay? So what we did here, the data set contains 1 million sessions, and we retrieved 200 candidates for each session to build that gradient boosting model. So 1 million times 200 will be 200 million rows in the training set. It's too much to fit, usually to fit in memory. So we decide to decrease the size. That's why we built the train set in only 1 month of data, in April of 2021. So using 1 month of data, we can reduce by 16 million rows the data set, contain 20 item candidates per session, right? So basically, we run that strategy here. We train the model in April, validate on May, and then we train the data in May and infer the test set to generate the submission, right? It's a little bit different than the previous validation scheme I passed before, because the previous one was used by deep learning models, and this specific one was used just for gradient boosting model. But yeah, I use a binary classification approach here. One detail. To build the candidate list for each session here, I use the statistical model I described first in the first model I described here. So I use a statistical model just to generate the candidates per session here, to generate the train set here. This is how it works. For each session ID, now I have 200 rows, right? Each row is a item ID, a candidate item ID. If the row, the item ID is the item purchase, I set the label as 1, the other labels all are 0, and it becomes a binary classification task. All the features I add here on the right can be based on feature engineering, any kind of feature you can think about that you can produce using the data given, right? And then, given the training set that I built, I run XGBoost and LightGBM. XGBoost optimizing a binary classification loss, and LightGBM optimize a lambda rank loss. As you may know, lambda rank optimized for ranking, and ranking is important on this task. And you see the lambda rank model will perform better when I show the model performance later. Model 4 is a multi-layer perceptron. It's a deep learning architecture. Basically, you feed the model with the item embeddings, item ID, like embeddings, and item features also like embeddings. Do you remember that I told that each item have features that represents the item? So we feed some feature information here as well, right? And in form of, the first layer is an embedding layer, and then we concatenate the layers passed by a full connected layers, and it becomes a session embed in the top. And that is very important step here. Once you have the session embed layers, we use a matrix factorization. We multiply the matrix of the embeddings of the item ID with the embeddings of the session ID in a matrix factorization way to generate the multi-class output for all the items in this challenge, right? But adding that, this is a multi-head, also multitask architecture, because adding to the item head, we added a matrix factorization for the user features head also. So we predict also the user features, so it have a multitask architecture here that can predict at the same time which item the user is tending to purchase, but also which item features the user is looking for based on the user history, right? Maybe the user is looking for a specific color or a specific size. This is part of the target here as well. Adding that second head usually helps to boost the model performance here. Okay, if you see in the model architecture, you see an event type flag. Also, this is event type flag helped to boost a little bit more the score. What is that? If it's 0, it means the model should predict which item will be purchased in the end of the session. If it's 1, then it predicts each item user will visualize next. It's 2 different tasks, right? Which item the user will purchase or visualize next. So at training time, we can set that flag 0 and 1 and change the task at the training time. Due to the randomness of the labels, we bagged that model 6 times. So using 6 different seeds to decrease the variance of the results and stabilize better the results and avoid some initialization weight issue with the deep learning models. We use transformers. Also, there's a NVIDIA library called Transformers for Rec, Transformers for Recommendation System. It makes available the XLNet transformer architecture. It was used here. Transformers are well known to predict sequences of events, right? And the same idea here, we feed the item embeddings from the user, the session history. And the output of the transformer is applied to a matrix factorization head together with the item embeddings here, right? From given in the first layer of the network, right? Usually that factorization machine head helps the model to combine multiple features and find interaction better between the features. And it's very used in Recsys solutions. Yeah, we also added that flag that I showed from the last architecture, the event flag predicting the next visualized item or the purchased item. It's the same here. Just adding that flag boosted by 0.003, the final metric. And the last and the best model for this specific data set was a recursive neural network. This, not exactly this architecture here, but a single variant of this architecture, but is very basic here. We use a GRU layer here for the item IDs in the user history, and we compare with all the 28 28,000 candidate items here, also using a matrix factorization head. This is a multi-class classification task, very simple. There's nothing special here other than we compare with all the 28K candidates items from the training set. But what we found better is not use the classical GRU approach, but use this approach here. Instead, using the output of the GRU layer, we pick the output of each GRU cell and do a weighted sum. Instead, we pick only the output of the last one. Doing that, the weighted sum of all users in the session history perform much better in the validation and in the test set. This gives us the best model, best single model in our approach. It scores 0.2044 in the leaderboard. It means, in average, a model can predict the right purchased item in the top 5 ranking, in average. Also, we found a post-processing step here, because, as I said before, if an item is present on the user history, in the user visualization, it should not be the label. So if the model outputs an item that is present on the session history, you should remove from the predictions of the model. Because for sure, any one of the items present on the session is not going to be the item purchased in the end. So with just adding that simple post-processing step can boost by 0.001 the metric. And here are the scores of each model. Statistical model around 0.16, neural neighbor-based 0.17, transformer for Rec 18, light GBM 18, MLP 19, and RNN 20 range. Those are all the 17 models we ended using in our stacking. Those are the metrics for all the models. Okay, again, talking about stacking. So I talked up to now about all those models here, model architectures here. So what I do now is I will pick 200 candidates for each model. So each one of these models will output 200 candidates. I will build a new data set using the candidates produced by each model, and I will feed the candidates to the second stage, right? That candidates were built on the validation set on the last month of the training set. And now I will feed to that 3 models on the stage 2. A XGBoost, a light GBM, and a weighted optimized average algorithm. There's some details about what kind of cross-validation we did in the validation set for each one of the algorithms. Basically, the weighted average, there's no cross-validation, but we optimize the original data set metric, the mean reciprocal rank at 100. For light GBM on the stage 2, we build a bagging approach. So we run 25 seeds, 25 splits, different random splits, splitting 85%, 15%, 25 times with different training seeds. Then we average the results of that 25 runs. And for XGBoost, we split by fold. In the validation set, we have 1 month, so we pick 1 fold for each week in the validation set, and each week becomes a fold, and we run 4 fold 3 times using 3 different seeds in order to decrease the variance and stabilize the results. Okay, so even in the stack, in the second level, we try to reduce as much as possible the variance of the results. And then finally, we pick the results of the 3 stage 2 models and just weight average the results. But the stage 3 models usually doesn't, it's hard to train a very complex model because it overfits very quickly. It's very easy to overfit on the stage 3 models because some leakage comes from the folding schemes from the previous stages when doing stacking. So we prefer to fix the weights on the stage 3. You use more weight for the more conservative algorithm. You use 0.5 weight here and 0.25 for light GBM and XGBoost. And then we just average the predictions with weights 2, 1, 1. And those are the final results. Stage 2, optimizing the 70 model weights, we got 20.73, XGBoost 27.4, and light GBM 7.6, right? And then when we averaged these 3 models, we got a bump to 0.282. And the final leaderboard, when they released the leaderboard after the competition deadline, we got very, very close results, 20.86, showing that we are on the right path. We didn't overfit our models, and we are calculating our metric correctly, right? This gives us a top 3 placement on the final leaderboard. And that's it for today. Thanks.
Fantastic. Thank you, Jiba. That was a great presentation. So I'm sure we'll have more questions than we have time. We only have time for a couple of questions, so but we'll make sure, obviously, people will be able to talk to Jiba afterwards. So we have one over here.
Hello, thank you for the presentation. I have a question. I noticed that on the second stage of stacking, the cross-validation, like the training scheme is not the same for the XGBoost and the light GBM. One is temporal split of the data, and the other is not. And as you emphasized the importance of the temporal split, I wondered what for the light GBM it was a random split. Is there a reason? And if not, do you think one of the two is better than the other one?
Yeah, we have the same question when trying to find the best validation split to run that stage 2 model, right? In the end, we found that any one of these 3 approaches scores very well, scored the same, the leaderboard about the same. The difference here is this stage 2 model was run in an out of fold in time from the validation set. All the data we run here is out of fold. We train the data in the previous month. We are running the validation, the stage 2 stacking on the next month, right? So all the data is out of fold. So there's no leakage in this case doing that because we know all the data, all the input features are out of fold, and all the data we have to train the model was that 1 month. There's no other way to do that because they're trying to predict the next month. So if you split by time or if you split randomly like the light GBM approach, it'll be approximately the same. In this case specifically, right? Because we're not overfitting to a long period of time, not 1 year of data, we're just overfitting to one specific amount that's very close to the test set. And that's why it works in this case, right? Not supposed to work at all the cases.
Okay, I understand. Yeah, I think we need to be flexible on this kind of rules. Okay, thank you.
Thank you. It's very impressive that we can implement so many good ideas in one competition.
Yeah. Thanks.
I have 3 questions. So first, you mentioned there are a cold start problem for item unseen. So is there any solution for cold start?
Yeah, there's some items, just a few items, but there are some items just first seen in the test set. For that items, we
will never predict this item.
Yeah, actually they are predicted, some of them are predicted, but why? Because some of the input features are the descriptions of the items. Sometimes the description is enough to tell what the user is looking for, right? And one of the models use also the description of the item as a target feature. So it can recommend even an item not present on the training set just because it's present, the description of the item is present as a target feature. It can be between the 100 guesses the model outputs, right? Yeah, but actually there's not much to do to that other than try to use the model, the item descriptions, right? Like color, size, or something else. Yeah.
Yeah, thank you. So the second question is in one session we have order of item. So the order information, how we embedding in the feature or how to use this information?
Yeah, actually, this specific challenge, as I showed, there's just a small number of items in the session. If I remember correctly, the maximum session length is 50 or something like that. But most of the sessions are only 3 or 4 items in the history, right? We have one input for each position in the model architecture. For example, the previous item is one specific input. The last one, the previous one is another input. The previous is another input. We encode it by position in one of the models, and the transformer can encode it as well using a position encoder automatically. Yeah.
Okay. And the last question is for the deep learning, the loss, which one you use? I think
it was treated as a multi-class classification, a default problem. So it's a multi-class loss, a default multi-class loss. Yeah.
Okay, log loss. Yeah.
It was, I don't remember it exactly, but we use maybe the default cross entropy loss. Yeah.
Thank you.
Yeah, it didn't change any loss function. It just didn't customize. It just using the default one.
Thank you for your time.
Okay, thanks.
Okay, that's all the time we have for questions. Please talk to Jiba if you have more questions. I'm sure there's so much in the presentation. So let's thank the speaker again, and thank you so much.
Thanks everyone.